All right, welcome to The Explainer. Today, we're going to tackle a core skill in chemistry, how to make salts. Now, I know it can seem a little complicated, but trust me, there's a really simple logic to it. By the end of this, you're going to have a complete mental guide you can use to make pretty much any salt you need to, step by step. Let's dive in.
So here's the plan for today. We're going to start with, what even are salts? Then we'll hit the single most important question you have to ask. After that, we'll walk through the 3 main recipes before putting it all together in one complete map. Sound good? Let's go!
Okay, so first things first. Before we get into the how, we need to be crystal clear on the what. What in the world are we actually talking about when we say a salt?
Now, you've probably seen salts out in the real world, right? Like these incredible salt deposits around the Dead Sea. But that's a whole mixture of stuff. In a chemistry lab, that's just not going to cut it. We need to be able to make one specific, pure salt. So we need a better definition.
And here it is. In chemistry, a salt is simply an ionic compound. That just means it has 2 parts with opposite charges holding it together. You've got your cation, that's the positive part, which usually comes from a metal or a base, and you've got your anion, the negative part, which comes from an acid. So really, you can think of it as a metal part and an acid part, snapped together like Legos. That's it.
All right. Now we're getting to the most important part of this whole process. This right here, this is the master key. It's the one question that unlocks which recipe or method you're going to use to make your salt.
Imagine this. You're in the lab, your teacher asks you to make some copper sulfate. You know there are a few different ways to do it, but they're all staring you in the face. How do you possibly choose the right one? Well, it all boils down to one single question. This is it. Is the salt you want to make soluble in water? The answer you give, yes or no, literally decides your entire path. It tells you exactly which method to use. So, you might be wondering, how do I know if it dissolves or not?
Well, we use these rules. Now, don't freak out and think you have to memorize this entire thing cold. Just look for the big patterns. Look at the left side. All salts with sodium, potassium, ammonium, or nitrate are soluble, period. That's a huge chunk right there. For the others, it's about learning the exceptions. Like, see how most chlorides are soluble, but there are a couple of troublemakers? Seriously, spotting the patterns and knowing the exceptions, that's the real trick here. It's like a chemistry superpower.
Okay, so you've asked the big question. And the answer is, yes, my salt is soluble. Fantastic. That leads us straight to our first method, which is perfect for a very specific situation.
Okay, so here's the deal with this method. You use it when the salt you want to make is soluble, but one of your ingredients, the metal or the base you're starting with, is insoluble. And it's that difference, the fact that one dissolves and the other doesn't, that's the secret sauce that makes this whole thing work. Let's take a look at how this actually plays out. See how they're adding that solid powder into the acid? The key here is to add way more than you need. You add it in excess. You just keep dumping it in until you see it sitting at the bottom unreacted. That's how you know for sure all the acid is used up. And then, because that leftover powder is insoluble, you just filter it out. Easy. What's left behind is just your pure salt dissolved in water.
So let's just recap the play-by-play. First, add that extra solid until the fizzing stops. Second, you filter out all the gunk you didn't use. Third, you gently heat the clear liquid you're left with to boil off some of the water and make it really concentrated. And finally, you just set it aside to cool down and watch as these perfect, pure crystals start to grow. It's a really satisfying process.
All right, on to method number 2. What if you want to make a soluble salt, but this time your starting ingredients are also soluble? Now you've got a bit of a problem, don't you?
And this is exactly the problem that titration is designed to solve. I mean, think about it. If your acid and your alkali are both just clear liquids, you can't just dump in extra of one, right? There's nothing solid to filter out. You just end up with a soupy mess of your salt mixed with whatever you added too much of. No good. You need a way to mix the perfect amounts.
And that's where this beautiful piece of equipment comes in. It's called titration. That long glass tube, the burette, is basically a super precise chemical measuring tape. It lets you add one liquid to the other, literally drop by drop, until you hit the exact point where they've perfectly canceled each other out. You use an indicator, a special dye, that changes color to scream, "Stop, you're done!" The end result?
No leftovers, no contamination, just pure salt solution. Super clean.
And here's the really clever part. You actually do this in 2 steps. First, you do a practice run with the indicator. That's just to find out the magic number, the exact volume you need. But you don't want that indicator dye messing up your final beautiful crystals. So you dump that out and do it all over again, adding that exact same amount, but this time without the indicator. That leaves you with a perfectly pure salt solution all ready for you to concentrate it and get your crystals.
So we've covered 2 ways to make salts that dissolve. But what if, when you ask that first big question, the answer was no? What if the salt you want is insoluble? Well then, my friend, we turn to our third and final method, which honestly feels a bit like a magic trick. The rule here is as simple as it gets. If the salt you want to make is insoluble, meaning it doesn't dissolve in water, this is your method. It's called precipitation, and it is beautifully straightforward.
Think of it like this. It's kind of like a partner swap at a dance. You start with 2 different soluble salts, both happily dissolved in water. But when you mix them, the positive ion from one solution sees the negative ion from the other solution, and they instantly decide they'd rather be together. And boom, they grab each other and form a new, insoluble solid that just appears out of nowhere. That solid is called the precipitate.
And the steps are honestly as simple as they sound. Step 1, pour 2 clear solutions together. Step 2, watch as a solid cloud instantly forms. That's your salt. After that, you just filter it out to collect it. You give it a quick rinse with some pure water to wash away any of the other ions hanging around, and then you let it dry. Done. It's often the quickest and easiest method of them all.
All right, we've walked through all 3 methods. We've seen when and why to use each one. This next part is where we put it all together into one single map. This is what you want to burn into your brain. This flowchart is everything. Let's trace the logic one last time so it really sticks. You start right at the top with the salt you need to make. You ask question number 1, is my salt soluble? If the answer is no, your path is super simple. You go right down this branch to precipitation. But if the answer is yes, you have one more question to ask. Are my starting ingredients also soluble? If the answer to that is no, you use the excess method because you can filter the extra stuff out. If the answer is yes, everything is dissolved, so you need the precision of titration. See? That's it. A simple 2-question process to get you to the right answer every single time. Okay, let's wrap this up with a real-world puzzle that puts everything we just learned to the test. We all know that, generally, barium compounds are toxic to humans. So why on earth is it safe for a hospital patient to literally swallow a barium meal that's full of barium sulfate before they get an X-ray? The clue to solving this is that very first, most important question we learned to ask today. So, what do you think? Why is it safe? Thanks for joining this explainer.